Okay, again, last time we were, I need to talk about capacitors. Um, if you have a fully charged capacitor and no source, then your current is going to equal dq dt. And your voltage is going to equal Q over C. So the current is voltage over resistance, which is Q over RC. So dq over dt equals Q over RC, except that the voltage, well, let's solve it. Okay, so we get this solution. Since the absolute value of Q equals having a rash of writing things down. We have this equation. I'll just integrate it. We get the natural log of the absolute value of Q equals T over RC plus an integration constant. I don't want to use C for the constant. So I'll just write out the constant. So the Q equals absolute value of Q equals E Okay, I do have to be careful with signs. Our equation is going to be dq dt is negative Q over RC. This is a positive direction and you have a positive charge here. It's going to drive current in the negative direction. And you're going to get this, okay? I'm just going to put the negative signs here. And that's going to give me a negative sign here. And a negative here. Negative here. The constant is an arbitrary constant, could be any number. So E to any number could be any positive number. If the absolute value of Q equals this, I could have an absolute value here, but taking away the absolute value, that allows Q naught to be positive or negative. Something you should be familiar with. So right there is the equation for the charge on this circuit. If we have a voltage, maybe an alternating current, maybe a direct current. So let's, for the moment, talk about alternating current just a little bit. So let's just assume we have a source here. And we have the capacitor here. Then Kirchhoff's laws tells us the sum of the voltage drops is 0. So if this capacitor has capacitance C, resistance is R, and the source is some constant voltage. And if we do a positive loop, our voltage drops are negative V plus IR plus Q over C equals 0. Again, I repeat every time, this just says that the potential difference between any point here and that point itself, in other words, well, the potential is the same at this point as it is at this point, which means if you go from this point around the circuit and back to this point, you have 0 change in potential. You do 0 work per unit charge. Okay, so this tells us that R dq dt plus Q over C equals V, the homogeneous equation, which we've done. It's basically this equation. And actually, I don't want to do that. I just want to separate this equation. Plug the homogeneous equation with RLC circuits. This tells us R dq dt equals V minus Q over C, or dq dt equals V over R minus Q over RC. So that might not be the most elegant way to solve this. Here's separable equations separated. We multiply by dt essentially, or just, dt goes over here. and it's not really a multiplication, but, and then we divide by the coefficient, and we get this. This tells us F is a natural log of V over R minus Q over RC. But if we were to take the derivative of this, integral would give us a negative 1 over RC. Okay? So that this equation gives us RC, natural log, and it's negative RC, natural log of this equals T. Skip the steps. We can divide both sides by negative RC, which will give us a negative T over RC. And dividing an arbitrary constant by RC is still an arbitrary constant. We just say the constant absorbs the division by negative RC. Then really appropriate to call this Q naught. I'm going to do it. I'll change it if I need to. Okay. So change from natural, doing the exponential of both sides. E to the natural log of this is this. E to this is this, just like it was over here. Okay. And we finally get these starting to look a lot like an RL, and that was a little surprising. Okay, so we get Q of T then equals I have to subtract V over R from this side and then multiply by RC. Have a negative, multiply by negative RC. Steps are straightforward, but that doesn't mean I don't split them up. Let's see. Go back to here. There's your voltage drop. There's the voltage. That big sides is all good. Negative Q over RC there. There we go. Have this. Derivative of this is this. Our C, get this. If we multiply through by RC, then also multiply this by RC. And that's where I think I screwed up. But this should have units of charge. RC doesn't. RC has units of reciprocal time. That's right, it has units of time. Well, we're here messed up somehow. You see any? Now CV has the right units. Capacitance times voltage gives you charge. Why does this not have units of charge? I want to say it's not. You understand what my problem here is? It's units. RC has units of time. Okay, we can work that out, but it has units of time, and it better have units of time since you need a unitless exponent here. Can't take E to a quantity that has units. It has to be just a number. And also you got to work on, R is reciprocal conductivity, which means this, which means that, and so forth. Okay. Said I would use Q naught here and deal with it. I needed to, and I need to. I'm gonna call this A. So labeling that Q naught is not appropriate because this side clearly doesn't have units of charge. Okay, so I should have taken the safe route and used this arbitrary constant there. Where A then is a constant to be determined. And it's going to have units of charge over time. So that this whole thing has units of time. Okay, so now RC times A can be anything. Because A is an arbitrary constant. can let the arbitrary constant equal CV. Let's let it equal CV. Just needed to make a TORC is what happens. And the interpretation of this is Q exponentially approaches CV, negative CV. Q equals CV, the voltage capacitor is Q over C. C is negative QV. Well, if the voltage here is V, when the capacitor is full, charge is going to stop because the capacitor is going to be pushing back the other way. And its voltage is going to be negative V, right? The capacitor is fully charged. When you're cranking, becomes infinitely easy. This thing has a charge that's opposite to this, a voltage that's opposite to this. And that's exactly what this says. And the graph, understand graph for calculus. So exponential approach. CV. And this being absolute value of Q is the negative, like the negative exponential horizontal reflected version of this graph. So this is what happens. You're charging up that capacitor, you're cranking along, and where do you have the greatest current? Well, the current is the slope of this graph, isn't it? It's a change in Q divided by change in T, which is the amount of charge flowing per unit time. So the graph is steep here, and it gets less and less steep as you less and less charge. You've seen that on the interface. You've seen that exponential curve when you're cranking or when you were using constant source, a battery or whatever. See this behavior, which could also be okay. And this shows why you have that behavior. And this is really straightforward if you don't make the mistake of using a Q naught here, which was a very bad idea. Okay. And I used Robert Trump constant, I would have seen that it's absorbed the negative RC here. And everything. Looks like. Okay. Your book also derives. It. Okay, well, that's important to understand about expense. Let's turn for a minute to magnetism because I'm talking about magnetism before we talk about induction. Induction. Notation is great to DS. I kind of prefer it. DA, vector A. But whichever. This is just the perpendicular component of the magnetic field to each this tiny element of surface and you add them all up. And we have an intuitive idea of what flux is. So that's the definition, develop that idea. So hopefully you understand it. So here's lenses in most of its glory. Okay. Now, this is done in the transition problems just by saying, okay, you got a flat region, it's at some angle with the magnetic field. What's the flux? Well, it's just the area times the magnetic field dotted with the normal vector, right? The flat surface, then phi b equals b dot m times the area, right? Surface is phi b equals phi b equals magnitude of b times the area times the cosine of theta, where theta is the angle between b and n. So we got b And England, here's fail. Match your intuition. This is what we actually use in the transition problems. But you've seen the rest of the notation in your text. And we've talked about it in class, but probably not as much of a song. Okay. Now, if theta equals omega t, then the rate of change of phi is this. This is just some constant, assuming omega is constant. And it's just a sine wave, so you get the sinusoidal thing. Now, what is this? Well, this is the voltage around the boundary of the surface. I'm saying that this integral, E dot dr, you know, when you multiply electric field by a displacement, you're going to get a potential difference. That's what potential difference is. It's the work per unit charge, go from here to there. Okay. Let's use your voltage around your boundary curve. Basis for power production. At least power production that involves driving a turbine. Okay. So that you have coil rotating within a magnetic field, or vice versa. And typically, well, I'm going to leave it at this. I won't get into the very details. The rest is pretty obvious. My grandson would probably cuss me out for that. Since he's a power systems engineer, there's a whole lot of complexity. Okay. And I don't have a handle on most of those complexities, although they follow pretty directly from the physics. The engineering details. But he's never asked me to build a power plant. So what can I say? Okay. And I've never actually toured one. I'm sure that there's a lot of neat things going on. Okay. And then how do you distribute the power? That's kind of what power systems engineers expertise is. It's not really with the turbine. It's then how do you distribute the power? How do you make it stick and all that? Okay. So this leads directly to that. So if you got a big magnetic field in a big area and drive this thing at 60 cycles per second, generate a lot of power. That's why you need a fuel. Nuclear, gas, coal. hopefully something that doesn't destroy the environment. Um, at least not any faster than we can handle it. Um, okay, is that kind of clear? Okay, that's where AC comes from. I mean, it also comes from that generator. The generator actually produces AC. It's got a rectifier circuit that we don't have time to talk about, okay? That gives you a positive current, no matter whether you think it's positive or negative. It used diodes and a clever little operation that when the current goes this way, this diode cuts it off, but it goes through this other diode in the opposite direction, which makes it positive. Okay. And you can look that up. The diode's just something that only allows electricity to flow one direction. So with clever combination of diodes and so forth, you can make that circuit into more or less a DC circuit. At least it's always positive. Now you know when you generate that thing, well, you're getting a sine wave and you're rectifying that sine wave. Okay. So it still gives you a pretty fuzzy signal, but it looks like this. Okay. Instead of this. Okay. All right. Well, that's related to power. Also, magnetic field. I'll use the equation with the sign in it and so forth. It's K prime times this. I think that's the notation that's used. Is R hat is a unit vector. R is a distance to the point. Your picture is input current I. Here's an increment L. Here's your point. Here's your R vector. And I think I might have that because your current's in this direction, right hand rule knife. So PL cross R is in this direction. Your right hand rule for currents is put your thumb in the direction of the current, fingers curl around in the direction of the field. So that should be it. Okay. And you can integrate this, forget the point, from negative infinity to infinity. So you get the field of a long charged wire. DL cross R depends on the coordinates of the point R. But instead of DL, I'm going to use DX. Instead of the cross product, I'm going to use DX. So it's going to come out something like this. You have your K prime I factored out. Got a DX cross R. It's going to have magnitude DX sine theta. This is a unit vector. So this cross product will just give you whatever DL is or DX times the sine of theta. And then you divide by R squared. And you use the coordinates of your point. What sine theta is. So I'm not going to go through the details of that, but that's what you integrate. Now you call that point XY or XYZ, whatever you want to call it. Okay. And your sample point down here is an X. So this vector is going to go from coordinate X 0, 0. Usually you're going to say this runs along the X axis. So you get the point X 0, 0 to XYZ. Okay. Just say to XY. So if you have, well, sample point here will be X star. Call this point XY, we won't mess with Z. This thing is symmetric with respect to rotation. So we just do it in the XY plane and then say, instead of XY, that's like X square root of Y squared plus Z squared or whatever. Okay. Then R equals X minus X star one on I plus one. Okay. So that delta X cross R, I mean, you could just do delta X cross R and write it out in coordinates. You're going to have a vector in the K direction is going to have to be perpendicular both to delta L and R. That'll take care of your dx sine theta and your R squared. R being just the magnitude of this vector. Plug all that into the equation, whatever form you want, and you get make it more fun, integrate from negative L to L so you have a finite wire. That's a harder interval. Okay. Depends on your taste. Definitely. Well, your book derives that, and you get a formula. I don't remember the formula, I can rewrite it, but I'm not going to take the time to do that now. Okay, since it's our last, and we're just reviewing, trying to give you the context for all this stuff, okay? And also get a feel of a loop of wire. And I'm just gonna draw a picture, you got a loop of wire in a current. And you get magnetic field at the center. Need to integrate or create motions. The axis. Radius ahead. You should be able to set up that interval. And that's pretty standard. And it's an easy interval to do, so you should be able to actually do it. Set this one up and you find you don't need the interval. But those are two fundamental situations. Remember, when you do this, take that interval here. We did it last year, so need to. Here's your R vector. And your magnetic field is going to be perpendicular both to the dx vector here and the R vector. So it's going to be like this. So the magnetic field is going to come back something like this at some angle. If you do it from the diametrically opposed increment, with another R vector, with another magnetic field. There's a delta B. Here's a delta B. Well, that delta B one and delta B two if you want. If you add these two, the horizontal components are equal and opposite, and you end up with a vertical component. Delta B, and that's consistent. The right-hand rule of the loop tells you that the field at the center is, you have a counterclockwise current, field in the center is vertically upward if the thing is flat. You go up the axis, it's still vertically upward. It decreases in magnitude. So you have that situation. So those are fundamental things about magnetism. Then once you understand that, it's not hard to understand the rule for a solenoid. Okay. And you amperes, well, I should talk about amperes. Um, Again, I'm just going to draw the picture and go back where I did this in class not too long ago. You go along this path. where the kind of break here just indicates that this edge is way away from the solenoid. Then you get the integral of the magnetic field around this thing is related to how much current flows through this path. Now, the current that flows through this path would consist of the currents of all these loops. So each loop contributes a current. And then by a symmetry argument, you find that the total integral of the magnetic field around this loop is essentially just magnetic field. The integral magnetic field around the loop is essentially zero everywhere except along this part of the path. Okay. Along this part, it's equal and opposite to what it is along this part. This part is so far away, you have essentially no field. So total. Okay, well, that's for solenoid. Going into detail, we get to inductors. Solenoid would be an inductor. A coil would be an inductor. A coil's where all the loops are centrally together, like the Helmholtz coils. Loops aren't spread out over any significant distance. You would just have this for each loop in that coil. So those coils are oriented like this. If your current is going counterclockwise, you're going to get a magnetic field in this direction. And that's from both ends. In the second coil, they're oriented the same. You reinforce that magnetic field, and as it turns out, you end up with a nearly constant magnetic field within a pretty good volume in the center of those. They're the center of those coils. Okay. And estimate that just with this. You got a solenoid where the coils are actually distributed over some distance. And I'm being a little vague about defining that, but you know what I mean, because we built one. Okay. Then you get the field of that solenoid. Because of Ampere's law. It's going to remind you of this. Then you have more basic idea that the force on a moving charge is QV cross V. Or F equals IL cross V. So this would be like for a piece of wire in a magnetic field. Get the force on the wire. This is the force on a moving charge, like an electron or a proton. Okay. This applies helical motion. And you need to kind of review those details. Understand. This is what gives you the force on the water. Or torque on the loop. You have assigned problems, so you know, pretty much all of these situations. You want to be sure you work them out. Review your work on those problems. But when I just look at even the idea of an electric motor where you've got a loop. And you've got an alternating current. Use that alternating current in the loop to react to magnetic field. Okay. And use a commutator to reverse the direction of the force as the loop passes 180 degrees and all that stuff. I'm not going to give you a test. I'm not going to ask you to design this thing, but you know, you want to understand those concepts. Okay. Um, and I talked about a solenoid. So in an inductor, has a magnetic field in the inductor. You probably can't read that, but it's obvious. An inductor essentially consists of a bunch of loops. And if there's a current in a loop, you're going to have a magnetic field due to that loop. Okay. And if you've got a bunch of loops like in a solenoid, you're going to have a pretty good magnetic field inside the solenoid. And if you put a chunk of metal in there, it'll enhance the magnetic field, maybe by a factor of 100. Okay. Or ideally, in many cases, you know, even 10 to the third. Okay. Anyhow, now if you got a change in current in an inductor, that implies a changing magnetic flux in the inductor. Implies a back EMF. The IDT. And you're familiar with the symbols, so we don't need to say too much about that. Incidentally, for lab on Friday, for last meeting, I've got an inductor box. Now, I think we tried to use it before. And I think something's a little haywire with it, maybe too much resistance or something. We're going to play around with it because gives you inductances all the way up to the tens of Henrys. Whereas the circuit board that we've been using gives you 8 millihenries. Okay, about a tenth of a Henry, hundredth of a Henry. Okay, so we get some pretty big inductances here, and we want to see how big inductances are combined with various resistances and capacitances. Gives various output circuits, and especially be able to predict the resonance. Okay, so that we can actually observe the resonance. Turn a little dial, watch the signal on our interface, and watch the signal go from here up a little bit, and then all of a sudden, boom, big circuit. Okay. Resonance is a big deal. So, okay, well, this then leads us to the idea of AC circuits or RLC circuits. Now, an LC circuit, sorry, LR circuit. It's like this, homogeneous equation is this. It's a separable equation. You get DI divided by R over L equals negative DT. And you get I equals I naught e to the R over LT. R over L has units of reciprocal seconds. Okay. Negative. Um, um, that would be, for example, if you have an inductor already with a current in it and resistance, which is unavoidable, and a switch. And this would create a current, which is exponentially decreasing. Okay. So you would have a graph of I versus T. Looks like this. LC circuit. The homogeneous equation would be this. And it's easy to understand that that gives you something like Q naught Q sine cosine of omega T. With omega equal T. This would be the natural frequency of the circuit. This would be the resonant frequency. So we could take an inductor and a capacitor, calculate its resonant frequency, generate signal at that resonant frequency, and see what happens. And that would correspond to a circuit that looks like this. Or let's say we have a charged capacitor, there's a switch in here someplace, and we close the switch. What happens when we close the switch? The capacitor discharges, running a current through the inductor. Okay. The capacitor doesn't discharge instantaneously, even if there's no resistance. Okay, if right now we have no resistance. Now we can't do no zero resistance in the lab. If we had superconducting stuff in, we could come pretty close, but okay. So we create a current here, but there's a back EMF that prevents the current from changing too quickly. Okay. So what you have is just time. Okay, the current starts increasing. Okay, so that's pretty steep, where it's increasing kind of fast, but it can't increase instantaneously, even if you've got no resistance. Okay. There's going to be a significant voltage resisting this thing. So it's going to increase less and less rapidly. So it's like this. And now when you get to this point, there's no change in the current. So you get no back EMF. Again, I'm explaining this wrong. No. Okay. So you got a current here, no back EMF, so thing starts discharging through the capacitor, right? But as soon as it starts discharging through the capacitor, magnetic field in the inductor begins changing, preventing you from charging the capacitor up instantaneously. So your current is going to go down. So until the capacitor's charged. And now the capacitor's charged opposite to where it was originally. So you're going to get the same thing happening like this. And you're going to get the sine wave here. Now, this circuit will never give you infinite current. It can't, because even when the capacitor is fully charged and the inductor is empty, the back EMF prevents too much current from flowing. So you get the reactance omega L minus 1 over omega C that we talked about last time. Now we're into stuff that we're talking about pretty recently. If you've got an RLC circuit, just take the homogeneous case. Ninety phase degrees ahead of cosine omega t. And this is a sine. This is the cosine. Sine's peak happens before the sine. Q, well, the derivative of Q has to be Q prime, right? The derivative of this is this. No, this is the antiderivative. This is Q general about basic antiderivative of this, right? And there's no integration constant involved. Reasons it should be obvious. Okay. So this is I think I got some wrong here. This is negative. Um, worry about that. In any case, this is what gives us our phasor diagram. Find out sine of omega t, right? Um, yeah, I think it's okay. Um, now what do voltage, not current, not a time, so wrap it up pretty quickly. This is I used cosine, very cosine here. Here VL is we don't have room to write it. Okay. And it's just negative omega times the sine of this. And here is BC, which is RI naught over omega, sine omega t. Okay. This is your phasor diagram. These things rotate. Your net is the vector sum of these, and we illustrated that last time. Okay. If VL is bigger than VC, your voltage is going to anticipate the current across your resistance. If it's behind, then it's going to lag. And hopefully, if we get a good sine wave somehow, we can observe that. Okay. We can manipulate. Like, okay. And if these things balance, then you have a resonance. Okay. And that's your RLC circuit. Now, I wasn't able to go over every detail, but I think between last class and this one, that we covered most of the main points. I have lab on Friday. If you have some questions, we can answer a few questions. Okay. And I might choose to just talk to you a little bit. Okay.